What an integral actually means. You've seen the integral symbol before. It looks like an elongated S, and it's one of the most important symbols in all of mathematics. But what does it actually mean? Let's start with a simple question. If I give you the speed of a car at every moment, can you figure out how far it traveled? The answer is yes, and the integral is how you do it. Imagine a car that's accelerating. At each moment, its speed is a little higher than before. If we graph that speed over time, the distance traveled is the area under the curve. That's the fundamental insight of integration. The integral of a function f of x with respect to x from a to b gives you the area under the curve between those 2 points. It sums up infinitely many tiny slices to get the total area. Let's think about it visually. Take a curve, like x squared. Draw rectangles underneath it, each with a certain width. The narrower you make those rectangles, the closer their total area gets to the true area under the curve. The integral is what you get when the width approaches 0. This is the Riemann sum. You divide the area into n rectangles, each with width delta x. The height of each rectangle is the function value at that point. Sum them up from I equals 1 to n. Then take the limit as n approaches infinity. When n goes to infinity, delta x goes to 0, and the sum becomes exact. That's the definite integral. But the integral isn't just about area. It has a deeper meaning. The integral is the inverse of the derivative. This is the fundamental theorem of calculus, and it's one of the most beautiful ideas in mathematics. The derivative tells you the rate of change at a single point. The integral tells you the total accumulation over an interval. They undo each other. Think of it this way. If you have a graph of velocity, its derivative is acceleration, and its integral is position. Derivative breaks things down. Integral builds things up. This relationship between derivatives and integrals is what makes calculus so powerful. You can go from local information about how something is changing to global information about how much has changed. Let's look at a concrete example. The integral of x squared from 0 to 1. Using the Riemann sum, we can calculate that the area under the curve is exactly 1/3. The integral from 0 to 1 of x squared dx equals 1 over 3. Here's how it works. The antiderivative of x squared is x cubed over 3. Evaluate that at 1, you get 1 over 3. Evaluate at 0, you get 0. Subtract, and you get 1 over 3. The fundamental theorem makes this easy. But integrals go far beyond simple areas. They surface everywhere in science and engineering. In physics, the integral of force over distance gives work. The integral of electric field over area gives flux. The integral of probability density gives the chance of an event. In engineering, integrals calculate the center of mass of an object, the moment of inertia, the total charge distributed along a wire. In probability, the integral of a probability density function from -infinity to infinity always equals 1. That's how we know it's a valid distribution. In economics, integrals calculate total profit from marginal profit, or consumer surplus from a demand curve. And in geometry, integrals give you the length of a curve, the area of a surface, and the volume of a solid. The integral of pi times the radius squared from one point to another gives you the volume of a solid of revolution. So the integral is really about accumulation. It takes a rate of change and tells you how much has accumulated over time. It takes a density and tells you the total amount. It takes a probability distribution and tells you the likelihood of an outcome. The integral symbol itself tells a story. That elongated S stands for summa, the Latin word for sum. Because that's what an integral is, a continuous sum. An infinite sum of infinitely small pieces. And the dx at the end isn't just decoration. It tells you which variable you're integrating with respect to. It's the width of those infinitely thin rectangles. The integral connects the discrete to the continuous. It bridges the finite and the infinite. It transformed mathematics when Newton and Leibniz discovered it independently in the 17th century, and it's been transforming science ever since. So the next time you see that elongated S, remember what it really means. You're looking at a continuous sum. An accumulator of change. The mathematical tool that connects rates to totals, the local to the global, the instantaneous to the accumulated. The integral is calculus's way of summing the infinite. And we use it every day to understand the world.